So let us look at some results of this model. So we started by using some of the plant lab measurements that we had and fed that to the model. And we compared 3 different optimization algorithms. The first one is what we refer to as a uniform optimization, which is essentially unaware of the topology. So it simply assumes that all nodes are equal, all the links are equal, and it divides the data accordingly. The second optimization algorithm is what I'll refer to as myopic. So this actually takes optimal decisions at each step of the way. So it will optimize push, then it will optimize map, and it will optimize shuffle, etc. But it's doing these one at a time. Okay. So it's myopic in the sense that it's looking only a short area. And the final algorithm is the optimization that I just introduced. So here we are looking at an alpha value of 0.1, which corresponds to a lot of data aggregation. And on the y-axis, we have the make span, and each bar is divided into the runtime for different phases. The green is the push, yellow is the map, then shuffle and reduce. So what we see first of all is that the myopic optimization does much better than the uniform. In particular, it's able to get rid of a lot of the push. So it's able to figure out that you should push as close as possible. But it still is paying a lot in terms of the actual map execution. And the optimization, since it does an end-to-end optimization, it's also able to bring down the map cost. Now let's look at the opposite end of the spectrum. Now here we have a high value of alpha, which corresponds to data expansion. So the input data is actually expanding a lot. Now what we see is that a lot of the cost is being paid in the shuffle and reduce operation. So again, the myopic does a little bit better, but the optimization, the end-to-end optimization is able to do much better in all the phases eventually, since again it's making a globally optimal decision. So what these results are showing is that the model-driven optimization is able to achieve good performance across different scenarios. Then we went ahead and compared it to Hadoop itself. Now Hadoop itself has built-in mechanisms to take advantage of some of this heterogeneity and topology. So as I mentioned, it has techniques such as speculative execution. If some node is slow, it may redirect the computation to some other node, etc. So it does some of these things dynamically on its own as well. So we looked at 3 different applications. This is word count, and again we compared uniform with Hadoop, Hadoop using all of its dynamic mechanisms, etc., and the optimized plan that we gave to it. Here we are again showing push, map, and reduce. Shuffle is actually overlapped with the map and reduce cases, so that's not shown. So again, we see that Hadoop reduces the push quite a bit, but it still pays a little bit in terms of map, which we are able to get rid of. Then another application we looked at is sectionization, where you give it a large number of web logs, and it tries to derive different user sessions out of it. So this is a pretty useful application for a lot of web providers where they want to look at, or e-commerce providers where they want to look at what sections it uses. And here, now we are more heavy on map and reduce, and again the optimization is able to do. And then finally, we ran full and inverted index, which is sort of the driving application behind the web search engines. And again, as we see, here reduce is much higher, but the optimization is able to get rid of the bottlenecks in the system. So to conclude, we first of all talked about MapReduce, which is a large-scale data processing environment, and it's meant to scale to large number of machines, and it's very well designed for running on cheap commodity hardware, and it has inbuilt fault tolerance and reliability. And so it's very well suited for large number of data analysis applications. It's actually a fairly fertile ground for research also. There's a lot of work which have looked at different aspects of MapReduce in terms of resource management, algorithmics, programming models. and there's also a lot of work still going on, which will continue to go on. And I presented sort of one point in the spectrum. Some of our focus has been on taking MapReduce and extending it to highly distributed environments. And last but not the least, I would like to thank many of my collaborators, particularly many of my students who have actually done most of the hard work on this, especially my graduate student, Benjamin Hines. In addition, I'd like to thank my collaborators, John Weissman from University of Minnesota and Ramesh Seetharaman from University of Massachusetts. And with that, I'll conclude my talk and take any other questions that you may have.
Let's give him the usual virtual applause. Maybe you answered all the questions, but please ask questions, yes?
So the optimization algorithm you're working on, so are you planning to take it to Hadoop?
Yeah, so actually what the optimization gives us is an execution plan. So that plan tells us where to place the data and where to execute the task. So we have made modifications to Hadoop to implement these plans that the optimizer is giving us.
Yeah.
And some of the results I showed were actually running on Hadoop.
So that is contributed to.
We haven't made it part of the official source tree yet, but we have sort of a local version where we have made these modifications.
Okay. So, but that is available as a patch to Hadoop, or?
Right now, actually, we haven't released it, but we'll be releasing it pretty soon. This is fairly recent work, actually. So we have just started publishing it.
Okay, thank you very much.